The demonstration that we just did showed us what a standing wave is. A standing wave is a wave that occurs as a result of interference that makes it appear as if the wave is standing still, hence the name a standing wave. Really, as we explained in the demonstration, it really involves waves going one way, waves reflecting off of a boundary and coming back the other way and interfering with the waves still going the first way. These standing waves, though, coming as a result of interference, only happen at very specific frequencies. We always get interference, but the interference pattern usually looks somewhat random. But at very specific frequencies known as the resonant frequencies, it makes it look like the wave is standing still. Now, what does a standing wave look like? This isn't the greatest diagram because I used Microsoft Word to do it. But you know from the demonstration that it really involves sinusoidal waves like this appearing to be standing still. You know that this spot right here, the antinode, really involves the string going up and down, up and down, up and down a number of times per second. Constructive interference. And then the node, which appears in between the antinodes, is complete destructive interference where the wave completely cancels out. Again, that only happens at a very special frequency known as the resonant frequency, and then multiples of that. As we saw in the demonstration, it appeared at about 5 hertz, and then at 10, and then at 15, and then at 20, but not in between. So exactly what are those unique frequencies at which these standing waves appear? What are these resonant frequencies, or at least what are the values of these resonant frequencies? Let's figure that out. The first standing wave that we saw in our demonstration looked something like this. We had one antinode, and we had 2 nodes. Remember, the antinode is the bump, the constructive interference. The node is the dip, or the destructive interference. So 2 nodes and 1 antinode. That was the first standing wave that we saw. The second one that we saw had 2 antinodes. And the third one that we saw had 3 antinodes. And if we kept going, we would see 4 antinodes and 5 antinodes and 6 antinodes and so on and so on and so on. I think the biggest one that we saw was, what was it, like 20 or 25 or 24 or whatever it was? I can't remember what the highest we went to. Keeps going, right? But the pattern will be the same, so we're going to stop at drawing 2 or 3 of them. Now, we want to figure out exactly what frequencies these standing waves appear at. So let's define the length of the string as L, the length of the guitar string as L, the length of the piano string as L, or the length of the string in our demonstration as L. And then let's determine what L is, the length of the string is, in terms of the wavelength. Let's draw a complete wave over here. In fact, more than one complete wave over here. And let's trace this wave through as we go through these 3 different standing waves to try to see exactly how many waves make up that length. We start right here. For the first one, we start right here. And we go through one entire antinode like this. How much of a wave is that? How much of a wave is that? Is that a full wave? Is that half a wave? Is that a quarter of a wave? Is that a third of a wave? No, not a third. It might be a third of this. Actually, it's not a third of this either, but it's a half, because this would take us to one complete wave right over here, right? So that's going to be 1/2 of a wave. We're going to say L is therefore 1/2 of lambda. We're going to rearrange that to solve for lambda, and we get 2 times L. So in other words, the wavelength is twice the length of the string. Now what about the next one? We start right here, and we trace it through to here. How much of a wave is that? That's a wave. That's a full wave, right? So we're going to say L is equal to lambda. Or we don't really need to rearrange that one because we've already solved for lambda, but just to make it nice and tidy, we'll solve for lambda and say lambda is equal to L. What about the next one? We're tracing this one through like this. We keep going through a full wave, and then here. So we go like this. That's going to be how much of a wave? 1.5. We're going to actually write that as a fraction, or as an improper fraction. We're going to say L is equal to 3 over 2 lambda. It wouldn't be wrong to say it's 1.5 lambda or 1.5 lambda, but it's going to be easier to see the pattern that we want to see if we write it as 3 over 2 lambda. So that's what I'm going to do. Rearrange that. 2 goes up, 3 goes down, and it becomes lambda is equal to 2/3 times L. And we could keep going, but we don't need to, because this is enough to see the pattern that we're going to see in just a couple moments here. Now what I want to do is take the wave equation. V is equal to F times lambda, or F is equal to V over lambda. Right, that's just the wave equation that we did a number of days ago, rearranged to solve for frequency. And what I want to do here is replace lambda with whatever I said lambda was equal to right there, in this case 2L. So let's take this 2L and sub it in right here for lambda. And I end up getting F is equal to V over 2L. That's the first resonant frequency that would occur in this guitar string, piano string, demonstration string, whatever the case may be. It would occur at whatever the speed of the wave is, divided by 2 times the length of the string. Now we can do a similar analysis for this next one. F is equal to V over lambda. Let's replace lambda with L. And we do a similar analysis with the next one. F is equal to V over lambda, but this time lambda is 2/3 L. Well, we can leave it like that if we want, but I want to simplify it a little bit, tidy it up a little bit. So I'm going to say instead of V over 2/3 L, I'm going to multiply by the reciprocal and get 3 over 2 V over L, right? Something divided by 2/3 is the same as 3 over 2. This frequency that we see right here is called the fundamental frequency. Or sometimes we call it the first harmonic. In fact, we call it a first harmonic, so we'll put a little 1 as a subscript there. That next one, take a look at its value. The first one is V over 2L. The second one is V over L, which is the same thing as saying 2V over 2L. So we get V over 2L, and then we get 2V over 2L. How does the second one compare to the first one? How does the frequency of that second one compare to the frequency of the first one? It's twice as much. If we double the first one, then we get the second one. We're going to call that one the second harmonic. In the second harmonic, F2 is equal to 2 times F1. Take a look at the third one. 3V over 2L. The first one was 1V over 2L. So the third one is 3 times the value of the first one. Therefore, we'll call that one the third harmonic. And we can write it out as 3V over 2L, or we can say F3 is equal to 3 times F1. I got good news and I got bad news. The bad news is none of these appear on our data sheet. V is equal to F times lambda does, but the V over 2L or the 3V over 2L or whatever doesn't appear on our data sheet. That's the bad news. The good news is, if you do it the way that I like to do it, the only one that you've really got to be able to deal with is the first harmonic. My suggestion to you when you solve these problems that you're about to solve is that you always go through the first harmonic. Let's say you're looking for a length of a string. You're given the frequency of the third harmonic. Divide it by 3 to get the frequency of the first harmonic, and then use the equation for the first harmonic to solve for the length of the string. Let's say you're given the length of the string, and you want to find the frequency of the 14th harmonic. Well, then use the equation for the first harmonic, get F1, and then multiply it by 14. You could derive the frequency of the 14th harmonic like we did the second and third here, but why bother? If we can deal with the first harmonic, we can always go through the first harmonic to solve for whatever it is that we're looking for. And I'll show you a couple examples of that in just a moment. Example number 1 says a 25 centimeter long string is set into vibration. The speed of the wave is 500 meters per second. What's the first 3 possibility for harmonics in this string? We could derive an equation for the first harmonic, and an equation for the second harmonic, and an equation for the third harmonic. Or you could take my advice, which was to always go through the first harmonic and then just find what you're looking for from that. So let's deal with the first harmonic first. I'm going to draw a picture of that, and I'm going to derive the equation because it doesn't appear on our data sheet. The more we derive it, the more likely we are to be able to do it on a test. This is the length of the string, and the length of the string is half of a wavelength. Lambda is therefore equal to 2 times L. F is equal to V over lambda, which is V over 2 times L. There's my equation for the first harmonic. Now let's calculate the value of the first harmonic. We're going to say F1 is V, which is 500 meters per second, divided by 2 times the length, which is 0.25 meters. 500 divided by 0.5, I believe gives me 1,000, doesn't it? Which we should, by rights, round to 2 digits, 1.0 times 10 to the 3 hertz. Done. There's the frequency of the first harmonic. We could do a real similar analysis to find the frequency of the second harmonic by deriving that second harmonic equation, or the alternative is we could just say F2 is equal to 2 times F1. 2 times 1,000 gives me 2.0 times 10 to the 3 hertz as my second harmonic. And F3 is 3 times F1, or 3 times 1,000, which is 3 times 10 to the 3 hertz. So you got options here, but if, take my advice, you'd find the first harmonic and then simply multiply it by 2 and multiply it by 3. What if we have a situation like this where it's not a string attached at both ends, but rather it's an air column, like a flute or a clarinet or a water bottle when I blow in across the top of it? We hear a sound. Well, the reality is when I blow across the top of it, there's hundreds of different frequencies generated in that water bottle or in that flute or in that clarinet, but most of them die out, just like they do in a guitar. The ones that stick around correspond to the resonant frequencies or the natural frequencies of that air column. But it's a little bit, the frequencies that occur in the air column, like the water bottle or the flute or the clarinet, are a little bit different than they are for the string. The equation ends up being a little bit different. What I want to do right now is derive the equation for the standing waves that occur in that air column. Let's draw it out, first of all. If we could see this, now keep in mind, I can't do a demonstration to show you this because this is air. We can't see the standing waves formed in air, but if we could, it would look like the standing waves formed in the demonstration that we did with the string. The first standing wave would look like this. Notice the difference. When we had a string attached at both ends, we had a node at both ends and an antinode in the middle. When we have a water bottle or a flute or a clarinet that's closed at one end and open at the other, then we get a node at the closed end and an antinode at the open end. It's just the way the interference takes place and the way the standing wave is produced. That would be the first harmonic. That would be the first one that we would see. The second one, if we could actually see it, would look like this. One antinode in the first one, 2 antinodes in the second one. And the third one would be 3 antinodes. And so on, and so on. 4 antinodes, 5 antinodes, 17 antinodes, 18 antinodes. We could keep going, but this is enough to see the pattern. Let's define the length of this. It's not a string this time, but a length of the air column, the length of the water bottle, or the length of the clarinet, or whatever it is that you're dealing with here, as L. We're going to say L is equal to, how much of a wave is that? I start right here and I go to here. How much of a wave is that? That's a quarter. Yeah, L is equal to 1/4 lambda, or lambda is equal to 4 times L. Next one, we go from here to here, or like this. How much is that? How much of the wave is that? This would be one complete wave. What we've just done there is 3/4 of a wave. So we'd say L is equal to 3/4 of lambda, and we want to rearrange that to solve for lambda. Take the 4 up, the 3 down. It would be lambda is equal to 4/3 times L. The next one, we're going all the way up to here. This would be 1 1/4 of a wave. 1 1/4, or writing it as an improper fraction so that we can see the pattern, we'd say 5/4 lambda, or lambda is equal to 4/5 L. So we're going to say F is equal to V over lambda. That's the wave equation again. But let's replace lambda with, well, in this case, 4L. Notice that equation is different than the equation for the first harmonic when we had a string. For a string, it was V over 2L. For this air column that's open at one end and closed at the other end, it's V over 4L. This would be our first harmonic, or our fundamental. Next one, we'd say F is equal to V over lambda, or F is equal to V over 4/3 L. To rearrange that, we would say, or just to tidy it up a little bit, we'd say F is equal to 3/4 times V over L. And for the next one, we'd say V over 4/5 L, which is the same thing as 4/5 times V over L. What do you notice about that second one there? Compare that second one's value to the first one. V over 4L, 3V over 4L. Is it twice as much? Is it 3 times as much? 3V over 4L is 3 times the value of 1V over 4L. Therefore, we're not going to call this the second harmonic. We're going to call this the third harmonic. Because it's 3 times the value of the first harmonic. What about the next one? Sorry, that shouldn't be 4/5. That should be 5/4, right? Which means that this one is 5 times the value of the first one. We call it the fifth harmonic. What about the second and fourth harmonic, and the sixth, and so on? There is none. There is none. When you pluck a guitar string, most of the frequencies die out, except the first, second, third, and so on harmonics in that string. When you blow across the top of a water bottle, most of the frequencies die out, except for the first, third, fifth, seventh harmonics. There are no second harmonics or even number harmonics in general for air columns that are open at one end and closed at the other. So, solving problems involving this, we do the same thing as we did for the string, except we go through the first harmonic, except that two differences here. One, the first harmonic is V over 4L instead of V over L. And then second, we want to find the second sound produced. We would multiply it by 3, because the second sound produced is the third harmonic, and then the fifth harmonic, and so on. So strings multiply by 2, 3, 4, 5. When we're talking about these closed air columns, we multiply it by 3, 5, 7, 9, 11. Otherwise, it's the same thing. If you can solve those questions on the first side of the page, you're going to be able to solve the questions on the second side of the page. Lastly, what do we do if we have an air column that's open at both ends? This would be like a pipe, right? It's got an open end at either end of it. Well, If we have an open end, we know that we have to have an antinode. So the first harmonic would look like this. The next one would look like this. 2 antinodes, 3 antinodes, and so on. I'm going to go through this one really quickly and only derive the equation for the first harmonic, and then I'll just tell you what the pattern would be. This is half of a wave. So lambda would be equal to 2 times L. F would be equal to V over lambda, which corresponds to V over 2L. Isn't that the same equation that we had for the string? Yeah, it is. That would be our first harmonic. This would be our second harmonic. It would be 2 times the value of the first. This would be our third harmonic, and it would be 3 times the value of the first, and so on. So here's the deal. If you get a string that's attached at both ends, or if you get a pipe-like thing that's open at both ends, in other words, if both ends are the same, then the first harmonic is V over 2L, and you have the second and the third and the fourth. If you get a situation where the ends are different, one end is closed and one end is open, like you get in the water bottle or most air or wind instruments, then the first harmonic is V over 4L, and there is no second, and then the third, and there is no fourth, and then the fifth, and so on. Regardless of the situation, though, remember, always go through the first harmonic. If you've got the seventh, get the first, and then do what you need to do. If you want to find the fifth, get the first, and then multiply it by 5. This doesn't matter how you get the first. It's a little bit different between these. Does that make sense? Okay, one more example, and then we are done for the day. Or I'm done for the day. You got some problems to work on, but it's the second one on the sheet that I handed out to you. It says, what are the frequencies of the first 2 harmonics observed in a 40 centimeter long closed air column? Closed air column, by the way, just means, doesn't mean closed at both ends. It means closed at one end, open at the other. An open air column would be open at both ends. An open air column, the first harmonic would look like this. That's the first harmonic. Why did I draw the first harmonic? Because I always want to go through the first harmonic. L is the length of the air column, and it's 1/4 of a wave. Lambda is equal to 4 times L. F is equal to V over lambda, which is V over 4 times L. The speed here, we don't know what the speed is. Somebody was asking me a question about this at lunchtime. When you've got a temperature, what does that have to do with anything? There's a nice simple equation that gives you the speed of sound given the temperature of the air. It's on your data sheet in the bottom right-hand corner. It says 331 plus 0.6 times T being the temperature. You're going to use that a couple of times on your assignment. Question number 1, I believe. And then I think maybe another one. So let's get speed, and then divide it by 4 times the length of the string. Let's get speed right now. 331 plus 0.6 times 30 degrees Celsius. 0.6 times 30 is 18, plus 331 is 349 meters per second. Let's say the frequency is 349 over 4 times 0.40. Can you board that? Let's do this math here now. 349 divided by 1.6 gives me 218.125 hertz, which we're going to round to 3 digits, which is 218 hertz. There's the frequency of the, what have I just found? That's the first harmonic. Now, what about the next one? Let's label that first harmonic. What's the next one I'm looking for? F2? F1? F3. Because there is no second harmonic when you've got a closed air column. So the next one is F3, and it's equal to 3 times F1. 3 times 218.125, which gives me 654.375, or 654 hertz.